In this video, we're going to use this example to motivate what we're going to talk about next in the class, which is controller design. So far, our journey through closed-loop control systems has really talked about stability, tracking, and a couple other topics. And so what we'd like to do now is, with controller design, is to address the fact that oftentimes we have time domain specifications that we would like to satisfy in addition to things like stability and tracking. And so we talked about stability in the second section of the class, where we were essentially quantifying what the time domain specifications of a response were. But now what we'd like to do is we'd actually like to design our controller to achieve time domain specifications. And so we'll review those in just a second. But what this is going to do is it's going to allow us to solve a problem that looks like this, where we have an open loop plant that looks like this, a controller that essentially has this kind of format, but we have adjustable pole locations alpha and gain k that we get to choose in order to help achieve our time domain specifications. And so we can solve a problem that looks like this, where we're going to pick the gain k and the pole location alpha so that our closed loop response to a unit impulse has an overshoot less than 25% and a 1% settling time of less than 0.1 seconds. And so these might be motivated by the various applications where this closed loop system might arise. And so because this is going to be closed loop behavior, it makes sense that we go ahead and compute our closed loop transfer function. And at this point in time, this should be second nature to get down to a transfer function that looks like this. When the reference is a unit impulse, then this is just 1. And so we're left with a transfer function where y is just this this transfer function here. And so one of the things that's worth observing before we get a little bit further is the different portions of the denominator polynomial that essentially are two variable knobs give us access to. And so what you'll see is that the controller gain k appears only in the constant term, whereas the controller pole location alpha appears both in the constant term and in the linear term. And that's going to affect how we're able to use those two different factors in order to achieve these two different time domain specifications. So next, let's review our time domain specifications before we solve the rest of this problem. So a lot of what we did from time domain specifications was motivated by just looking at a simple second order system, essentially a set of poles that are potentially complex. And what we were doing is we were mapping these from essentially a stable real part and an imaginary part omega, and finding these two locations in the complex plane and then computing the transfer function that corresponded to those. And what we did is we parameterized those. We chose to parameterize those with a damping ratio and a natural frequency, this omega n squared. And what that led us to is a generic format for when we look at these systems in terms of this natural frequency and this damping ratio. And there were geometric ways of understanding that, is that the natural frequency was essentially the distance, the direct distance from the origin out to these poles. So it's that straight line distance. And the damping ratio is related to the angle here. So this angle is theta, but that's directly related to this damping ratio. So the smaller the damping is, the smaller this angle. And so that means you're going to be closer and closer to this imaginary line where there is no damping. And then once you're at 90 degrees here, where theta is equal to 90, damping ratio gets to 1. And that means that's the maximum damping you can have, because there's actually no more oscillation at that point, because then you'd be on the real line. So this was all motivated from this second order system interpretation. And so in that context, we were looking at essentially the response, and the response had to do with quantifying these four and also the steady state, and that's really the tracking. So the time domain specifications boil down to these four quantities, and in some cases, the peak time and the overshoot, we were able to come up with exact criteria. Otherwise, in terms of the settling time and the rise time, we have these rough guidelines that come from approximations. And so what we're going to do is we're going to use, in this case, we have a settling time domain quantification. So in this case, the percent settling is 1%. And we also have a peak overshoot quantification or time domain specification that we'd like to achieve. And so we're going to use these two formulas in order to figure out, back calculate what acceptable values of zeta, this damping ratio, and this natural frequency omega n can be in order to give us the values of k, the gain k, and the pole location alpha that are going to satisfy our time domain specs. Okay, so we'd come down to here, and so what we're interested in doing then is to take a look and compare this generic denominator here with the denominator that we have in our closed loop transfer function. And what we observe is the fact that this linear term here is 25 plus alpha. And that means that our variables 2 times zeta times omega n should be equal to 25 plus alpha. So that's another way of making a direct correlation between that linear term and this linear term. Likewise, our constant term is 25 alpha plus 100k, and we can say that that should be correlated here to our omega n squared. So we can say the square of the natural frequency is 25 alpha plus 100k, and that 2 times zeta times omega n is 25 plus alpha. So we can use these quantities when we're going to try to calculate out our time domain specifications. So when we talk about our settling time, this was our formula minus the log of natural-based log, the E-based log of 0.01, because this is the 1% settling time. So that numerator is 4.6. And then what we notice is we have this zeta omega n. And there's lots of ways to substitute in for this, but one of the things you'll notice is that this linear term is 2 zeta omega n, so all we need is half of that. So that's when we substitute in for that, that's going to be 25 plus alpha divided by 2, because that's essentially this whole term divided by 2, and that'll give us just this term zeta omega n. And we're going to force it to be less than or equal to 0.1, because that's our time domain specification up here. And so when you rearrange this inequality, that gives us a constraint on alpha, which is the pole location, and it tells us that alpha needs to be greater than 67. So when alpha is less than 67, that means that we're not going to achieve this time domain specification. And so this is a way of guaranteeing our time domain specification for our settling time. And now we can take a look at the overshoot specification. Similarly, what we're going to do is we're going to write down our time domain specification for overshoot, and that says that this formula has to be less than 0.25, because again, this is our time domain specification for overshoot. And so in this case, it makes sense to go ahead and back calculate, just calculate from this equation what the value of zeta is, because this is all in terms of zeta, this damping ratio. So then we can calculate a damping ratio constraint, and we get from this inequality up here, we get the fact that this damping ratio should be greater than 0.4037. And so now what we can do is we can look and try to evaluate what the zeta value is in terms of what we have in these different terms. And so in this case, again, a couple of different ways that you can substitute these in, but what we're observing here is that we have this expression that 25 plus alpha has to be equal to 2 zeta omega n. And so what we've done is we've solved for zeta here, divided by 2 omega n, and that's where we get this expression right here. And now we can use this equality to substitute in square root of 25 alpha plus 100k for omega n in the denominator. And now we have an expression, and now another equality that says, okay, this is what we learned from zeta from our overshoot formula. So let's go ahead and put that in place, and we already have a constraint on alpha, and so then we could use that to specify what k is. And so what this is telling us, if we solve for k, we get this somewhat complicated formula. And essentially what this is telling us is that we can't design alpha and k independently. Once we pick alpha to satisfy the settling time, then that changes what values of k are acceptable. And so depending on how big we select alpha, so we know that 67 is an option, but we said that any alpha greater than 67 is an option. So that means that that may change what the values of k are acceptable. But if we do choose this 67, we can plug in 67 here and here, and that'll calculate out the fact that k needs to be less than 113. And so this now tells us design guidelines in order to achieve our 2 time domain specifications. And so that's one way to solve this out, using these assumptions about these formula. What ends up happening is, because we're using this approximated second order formula, these aren't going to hold exactly. These are essentially guidelines. So what we're going to do is we're going to fuse these intuitions that we get from interpreting the second order dynamics using the damping ratio and the natural frequency. We're going to fuse that with some geometry about the poles and our knowledge about how those poles change if we change either our gains or our pole locations or our zero locations. So it means that what we're going to do is we're trying to bring everything together, bring our knowledge of the root locus together with knowledge of how the root locus changes when we change the graph or the transfer function with poles and zeros, and then bring into it a geometric interpretation of these different time domain specifications. And so what we're going to see is we can see these time domain specifications as different geometries in the complex plane where the root locus lies. And so bring all of that together is going to make a way for us to do controller design based on these kind of approximate guidelines that will then allow us to apply them to more and more complicated systems.